exploit techniques, we will talk, we'll broaden the discussion to talk about vulnerabilities other than stack buffer overflow. Right? So far we have been saying, hey, here is a stack buffer overflow, how you can use that to carry out various attacks. So now we are going to talk about other types of overflows. Yeah?
Are the gadgets always at the same address, or does stack randomization change them?
So we will talk about randomization in maybe next lecture or the following lecture. I'll answer that at that time. Yeah?
So what exactly are the registers EX, EBX, and disable? Are they executed sequentially?
So since they are registers are, I don't understand the
I
question.
mean, the contents in those registers, are they executed by the system sequentially after
No,
the?
no. So the registers contain arguments to system calls. Okay. So if you do man something on your Linux box, it'll tell you the documentation for a particular system call. It'll tell you these are the arguments. Okay, and then the first argument will go into EBX, the second argument will go into ECX, and so on. Okay, so it's just an interface. Any other questions? Okay. So instead of having a buffer overflow on the stack, you can also have a buffer overflow in other regions of memory, and you can have it in the global variable section, or you can have it in the heap. Okay. So we'll talk about heap-based buffer overflow, and when you hear about heap-based buffer overflow, the first thing you might think of is, hey, what about just overwriting data and then overwriting the pointer? Okay, just as what we do on the stack. There is a local variable. You write past the local variable on the code pointer that's on the stack. Now instead you do that on the heap. Okay, so you can do something very similar, but the program needs to have a particular structure. So in this case, here is a structure in C which has some variable, right, some buffer or character array, and then it has a function pointer in there. Okay, so you can immediately see why it's like this, because this way, if I overflow past the end of this buffer, then the attacker will be overwriting a function pointer. Okay, so if the attacker overwrites a function pointer, then that allows them to hijack control flow when that function pointer is actually used by the program. Okay, so again, remember the attacker can only do memory corruption. Okay, what happens after the memory corruption is still governed by the original program, right? So in the case of stack smashing, the attacker overwrites the return address, but still nothing happens until the program returns, right? Similarly here, the attacker can overwrite this function pointer, but nothing will happen until the program on its own uses that function pointer, right? At the point where it uses the function pointer, then the attacker is able to take over control. So here is an example of a program code that's vulnerable and can cause this. So what this piece of code does is some function that takes two string arguments, okay? And what it does is that it copies those string arguments into this buffer, and then it uses this function. So in this case, of course, if the attacker was careful, I'm sorry, if the programmer, not the attacker, if the programmer was careful, they would have actually checked that this two calls will not lead to a buffer overflow. Okay. So, but well, they omitted this check, or they forgot about the check, and as a result, this strcat can overflow past the end of this buffer, and then can end up overriding that function point. Okay. So here is a example. Okay. So this shows an example, right? So here is the structure and the content of the structure. So out here, we are showing the location where the structure has been allocated, right? So when you allocate it on the heap, somehow it gets allocated at some memory location. Okay? So that is, it is that memory location, and it is this content. Okay. So originally it contains file : / foobar, and those of you who can read, can you read hex into ASCII? How many of you can do that? It's not that hard, at least, especially towards the beginning of the alphabet, right? Because so hex 6.1 is lowercase a, and hex 6.9 is lowercase I. So I can read up to in the first 9 letters. So the other thing you need to remember is that because of this byte ordering issues, right? So the first byte in a 32-bit quantity is going to be over here. Okay, so this F is this one, right? 6.6, and you can see that. Okay, so that is the 6th character, because the first character is 6.1. F is the 6th character, so this is F, and this is 6.9. So I told you it's I, and this is L. So you can say I, J, K, L. So that is 12, right? So 6C, and then this is 6.5, which is F, right? So that way, this contains. You can go through this and convince yourself that it contains this information. Now, suppose the attacker passes in these 2 strings as 1 and 2 in the previous. Right. So you have. We assume that the attacker controls either 1 or 2. Right. Let's say the attacker controls just 2. Okay. So now, once this is provided, you can see that you can see from here, right? So this is 4 bytes, 4, 4, 4, right? And then here is the last field, which is the function pointer. Okay, so that means that in this particular case, the buffer is 16 bytes, right? So 4, 4, 4, 4. So that's 16, right? So the buffer is 16 bytes, and so you can see that this is already 7 characters, and this is definitely more than 9. Right? So therefore, if you write this and then follow that with that string, you would overflow this and then go into the function pointer. Okay. And at that point, the attacker can control and make it point over here. Right. So in this particular case, you can see that this is still 0066 something. Right. So that is not going to be in here, because in order to point back inside the buffer, it should be starting with 0035. Okay. So the actual exploit cannot be this. Right. This is some string that will corrupt the CMP pointer, but it doesn't have, the attacker hasn't successfully made it point to something that they want. Okay, so I don't quite remember what you need in order to make it point over here, but since the attacker can control this, then the attacker can make it point to the beginning of the buffer, and now assuming that this piece of data is executable, when the program uses that function. Again, remember that this program happens to use that function after the copy operation. Right? So at this point, the attacker will, because the attacker controls the value of this function pointer, it's the attacker's code that can execute at this point. And whatever we said about non-executable code and so on, that still applies. So if, let's say, if the data is not executable, then at this point, the attacker has to launch a code reuse attack rather than a code injection attack. Right? So instead of making this point over here, they need to essentially make it point to existing snippets of code and execute a route chain in order to carry out the attack. So this is sort of the simplest form of a heap overflow attack. And you can see that there's nothing specific about the heap in this particular case. The very same problem can happen even if this is a global variable, right? Because we really aren't making any assumption that this piece of data is allocated on the heap. Right? No matter where it is allocated, if there is an overflow on this buffer, it will overwrite this function pointer, and then at this point the attacker will take over the overflow. So that brings us to another version of heap overflow, which is actually specific to the heap, and it's not something that happens on other memory regions. Okay, so we'll talk about that second type of attack, which is called heap metadata overflow attack.